This conference will now be recorded.
Welcome everyone, and thank you for joining us today. I'm Scott Jensen from Ute Light Corporation, and today the Expanded Shale, Clay and Slate Institute is presenting Stormwater Solutions with ESCS Engineered Media with Eric Nelson of Arcosa Lightweight, Chuck Friedrich, and myself as featured speakers. And just a little bit about the ESCSI. ESCSI is an international trade association for manufacturers of rotary kiln produced expanded shell, clay, and slate lightweight aggregate. ESCSI promotes the extensive use of rotary kiln produced lightweight aggregate in the lightweight concrete masonry and structural lightweight concrete markets, as well as use in asphalt, geotechnical, green roof, horticulture, and water treatment applications. Just a few housekeeping notes before we begin for the attendees. Please mute your audio and turn off your cameras. If you have any questions during the presentation, please type them in the chat box. And with that, we will get started. So the learning objectives for today are, give me just a second to turn off my camera. Understand the characteristics of ESCS Engineered Media and why they are important for stormwater media success. Learn how stormwater bioretention can be landscape features when the media is designed to infiltrate, drain, and reaerate root zones. And we're going to learn from some sample stormwater projects. The EPA is promoting green infrastructure as cost-effective, a resilient approach to managing wet weather impacts that provide many community benefits. While single-purpose gray stormwater infrastructure is designed to move urban stormwater away from the built environment, the green infrastructure reduces and treats the stormwater at its source while delivering environmental, social, and economic benefits. Stormwater is a major cause of water pollution in urban areas. When rain falls on our roofs, streets, and parking areas, the water doesn't soak in as it should. Stormwater drains through these gutters and storm sewers and the other engineered collection systems and is discharged into nearby water bodies. The stormwater runoff carries trash, bacteria, heavy metals, and a litany of other pollutants. Also, higher flows resulting from those heavy rains can cause erosion and flooding in urban streams, which can damage the habitat, property, or even the infrastructure itself. So the green infrastructure uses vegetation, soils, and other elements and practices to manage water and create healthier urban environments. So lightweight aggregates are produced using the rotary kiln method, where clay, shell, and slate are heated at high temperatures. At those temperatures, gases and vapors inside the material cause it to expand or bloat, hence the name expanded shell, clay, or slate. You can see from the pictures a couple of examples of the rotary kilns that are used in the process, as well as a look inside the kiln when the material is red hot and heated. The common gradations for the lightweight ESCS material are fines, which include the different sand sizes, the 3/8 or pea gravel sized material, and 3/4 inch coarse or gravel sized material. Other materials sizes are available depending on the location and the manufacturer. As we look at the total manufacturing process, you can see that essentially the raw material is mined, sized to be fed into the kiln, heated at high temperatures, cooled, screened and sized to industry specifications, and then shipped to customers and projects throughout the country. You can also look at the heating process from the fuel source, airflow through the kiln, and the air quality control that's in place to meet the air quality standards. This entire process is constantly monitored and tightly controlled to ensure quality and consistency. Given a little bit of history of the aggregate and expanded shell, clay, and slate, the characteristics were first discovered by a brick maker, Stephen Hayde, in 1908, when bricks made of certain clays actually puffed up under high heat, as illustrated in the picture there on the right. He was issued a patent in 1918 for ESCS created by the Rotary Kiln process. The early trademark name was Haydite. Manufacturing started around World War I to aid in shipbuilding due to the shortage of steel at the time. On the picture there on the right is the USS Selma, which was made with lightweight concrete and launched in Mobile, Alabama in June 1919. Lightweight aggregate use became widespread after World War II, and the expanded Shale, Clay, and Slate Institute was founded in 1952. Here's a couple illustrations of early uses of lightweight expanded shale, clay, and slate in concrete-related applications. This is a World War II concrete ship passing under the Oakland Bay Bridge. Both the ship and the bridge had lightweight concrete. On the right there is the Southwestern Bell telephone building built in 1928. The first building was structural lightweight concrete, which consisted of 28 floors. Today, lightweight expanded shale aggregate ESCS materials are available throughout the United States, with producers being able to service the entire United States as well into Canada. Lightweight ESCS material is all around us, from the roads that we drive on through construction and the maintenance of those roads, as well as geotechnical fields, sports fields and other parks, horticulture, hydroponics, aquaponics. It's all around us in our structural lightweight concrete high-rise buildings and bridge decks, lightweight block, other masonry units, stone veneers, and a litany of other applications, including stormwater, as we're addressing today. Some of the benefits of the material with regards to stormwater: one of the key things is it's light in weight. It's about half the weight of normal rock, sand, or topsoil. It's porous, which is important to add porosity to the soil, helps balance the air and water in the soil profile. And it also is important with the microbial activity that it helps promote and sustain with the management of the stormwater and treatment. It's structurally stable and strong. The angular particles will interlock. The gradation is set that such it won't break down. It doesn't degrade. Even in harsh weather conditions, it's going to remain intact. The material can absorb and desorb nutrients and water as plants need them. It can be very high draining, and those drainage rates can be adjusted to meet the needs of a project or a stormwater application. Most importantly, as we mentioned in the production process, it's consistent, it's produced in a controlled environment, it's pathogen-free, weed-free, and clean. Also gives us a high insulation value, which is important in moderating soil temperatures and maintaining the porosity of the material itself. And finally, it's sterile and inert. It's weed-free, it's chemical-free, and it has a high cation exchange capacity, meaning that it'll be very beneficial in exchanging ions in the soil and holding on to nutrients. This is a close-up of the porosity of the particle on the material. You can see the network of pores throughout, which is important for the absorption and desorption of the water and nutrients, and also to maintain the beneficial microbial activity and provide a place for those microbes to live. This illustration shows the higher porosity associated with ESCS materials as compared to traditional aggregates that have a lot less porosity. So why the materials work? They have a long history. They've proven themselves in use in rooftop gardens for many years now, which are some of the harshest environments and intense projects where it can be. They hold on to moisture and nutrients and absorb and desorb those nutrients as needed by the plants. They hold water longer than sand and provide soil temperature moderation, which can be important in areas of high heat or in areas where there's extreme cold temperatures. And importantly, they provide flexible design for infiltration rates. And those rates can be maintained in the future, even years down the road. You can see how the infiltration rates can be adjusted by using either fine graded or coarse graded expanded shale, clay, or slate, and or adjusting the proportions of the other soil components. And with that, I'm going to turn it over to Eric Nelson with Arcosa, who is going to go over some additional properties as well as get into a couple of projects using these materials.
Okay, let me redirect my slides here. Welcome, everyone. So starting off, basically what we learned in soil science class, we have 3 different particle sizes, beginning with sand, silt, and clay. Sand is the largest of all particles. It drains very well. It does not compact. It holds water, but not for a very long time. On the extreme end, you have clay, which is a very detriment to stormwater because it compacts very easily. There's a lot of surface runoff, very low permeability. The good thing about clay, it does hold water for a long period of time. It also dries out very fast and cakes up. So if you were looking at expanded shale, clay, or slate, in comparison to sand or clay, it basically falls in the middle. It drains very fast, high permeability. It holds water longer than sand. There's a lot of void spaces for the water to penetrate, and it does not compact. Looking at this table, sand drains at over 1 inch an hour. At the lower extreme, you have clay, which drains at a little over 1/10 of an inch an hour. From the diagrams below, you can see where sand is basically a vertical column of water penetrating the soil. Loam is evenly distributed, and clay basically sits at that top layer and spreads out and evaporates pretty quickly into the atmosphere. We took a sample of expanded shale, which is a 3/8 inch in size, and we blended it with 50% black screen dirt, which is the closest thing we could get to topsoil. You can see the gradation there of sand, silt, and clay, and the gradation of the expanded shale as well in blue. The USDA textural classification came back as a very gravelly loam. The infiltration rate of that was 24 inches an hour, compacted to 5.7, 0.5 feet per pound per square inch. If you wanted to modify that to get a higher flow or reduce flow, it's a simple equation of using more lightweight or a finer gradation of lightweight in conjunction with sand or compost. So basically, we look to mimic forest soils where they have more avenues for air and water. Urban soils are easily compacted from pedestrian foot traffic, machine compaction. There's a history of construction debris underground. It really limits the air and water infiltration into the soil. So in stormwater, we have basically bioretention and bioswale media. I'm going to talk about 6 projects that are in the DFW and Austin areas. The first one here is the green at College Park, University of Texas at Arlington. This was one of the first sites certified by the Sustainable Sites Initiative in 2012. It occupies 2.6 acres, which includes a gathering plaza, activity lawn, promenade, water detention system, which is the main attraction for this site. It reduces stormwater runoff by 25%. It filters 80% of the suspended solids. You could see there the bioretention media design. 1 part compost, 1 part expanded shale, 1 part native soil, and 2 parts sand. Looking at the overhead plan here, you start on the north side, the left side of the screen. where they designed a bioretention swale that runs along to this point here, where it enters a filtration zone with horsetail reeds running along the avenue here. Is basically 6 foot wide and 3.5 foot deep. It enters a bioretention system at this point. One thing to mention here, 1/3 of the storm drainage at the university here comes into the stormwater structure at this point here. In a big rain event, there's actually water coming out of that structure, backing up into the lawn area. It also goes underneath this pathway here to the bioretention system, where it slowly infiltrates into the ground. There is a check dam on the southern end of the bioretention system before it hits the overflow. These are some pictures. The upper left starts at the building, the bioretention cell. It moves to the south, where it enters the horsetail reed area, as I'm calling it, which does a great job of filtering the pollutants as it goes to the south. It does enter that bioretention cell at the lower right-hand corner. You can see underneath the pavement on the other side of that walkway, you do have the outlet structure as shown in the upper right-hand corner. So water is coming out of that structure in a big rain event. And this is really unique because you're basically taking water out of a drainage system, reducing the runoff, again, delaying input into the drainage system and improving water quality as it backs up under the lawn, the bioretention cell. The shot on the lower left was taken about a year after construction. The one on the lower right is about 4 or 5 years after construction. There's no irrigation on this project. About time to do a little cleanup. Here's a check dam on the lower southern end. The water does back up about 2.5 feet in the bow cell in a big rain event, but before it enters the drainage system as shown in the upper right-hand corner. Shoal Creek restoration is a great example of reducing runoff, delaying input into the drainage system, and improving water quality. This happens to be adjacent to a park. You can see a concrete trail there along the creek bed. To the left, there's a construction site, which I'll talk about here. The problem they were having with this project was runoff from the uplands residential area. There were 3 culverts are underneath the road parkway in 3 separate spots. So you had a lot of nitrogen, phosphorus runoff, basically sheet flowing across the parkway into the Shoal Creek area as identified in blue. What the designers did, they had opportunities in the tree clearings to basically swale out some areas and create detention basins using expanded shale and compost tilled into the soil to slow that water down, to catch it. In between the 2 biocells, you have a series of check dams. There's a swale there that, again, is the main purpose is to slow down that runoff, cleanse it on its way down before it enters the creek. Here shows some signage along the trail system, educating people about what they're doing along the project site. In the lower bottom of the slide there, you can see where the water is allowed to pool into those areas. Again, because this is a passive park, nobody's using it at that point in time during a big rain event. But this does a good job of capturing the first flush of pollutants. Here you can see one of the areas. This was amended with 3/8" expanded shale and compost. Upper left-hand corner is a picture of the mix going in. They did use temporary irrigation to get the turf up. Didn't take very long because, again, the moisture holding capacity of the lightweight aggregate and the compost did a good job of getting that turf up and running. This was a project done southeast of Dallas along Deep Ellum. This happens to be an area with a lot of restaurants, bars, nightclubs, and shops. This is a multi-block beautification effort by a firm in Dallas, K. Cook and Associates. The design of this bioretention system was done by Dr. Fawad Jaber with Texas AgriLife. Basically, this system is comprised of 50% plant-based compost, 25% expanded shale, 25% native soil. That tends to drain approximately 50 inches an hour. Beneath that, you have a 12-inch retention zone made up of pea gravel. So in a big rain event, you're getting good drainage through the detention filtration zone. It's allowed to back up into that pea gravel until it reaches that perforated pipe and goes out. That bioretention mix will stay moist for a long period of time, especially at the lower zones of that. And it provides a deep rooting bed for trees, plants. Lindsay White, who was a landscape designer on the project, I have to give a shout out to her. She did an excellent job with a presentation online that you could access called Soils, Lid, and LAs. It does a very good job of talking about the project and the process. This is one of the slides from that project where she talked about ripping the soils down to natural soils. They were ripped deeply and amended and stratified layers using, again, topsoil, expanded shale, and a mature finished compost, thereby restoring the soil structure and the permeability infiltration greatly increased. Here you can see other shots along the boulevard there with the curb cuts allowing for drainage into those biocells. Another shot of it here. So this is a project at DFW Airport Logistics Center. There's a lot of pavement on the project, a lot of sheet flow runoff. The designers on this chose to basically do a blend of 3/8" expanded shale and sandy clay. This was installed in a 6-inch depth. If you go back to your rational formula, you know that you're basically improving your coefficient of runoff with a higher permeability of this bioswale mix. And this is something that could be blended on site as long as you have a clean work surface to do it. It's basically volumetric blending 1 by 1. This is a shot finished afterwards. This is basically a 650-foot long swale in one direction. It goes off to the left side of the screen here, another 200 foot. And as you can tell, there's only one catch basin that basically collects this water before it is drained to the outlet structure. AT&T Stadium, this is a dual purpose use, overflow parking and also infiltration media. This was designed back in 2009. It's still up and running today, functioning very well. The designers on this were trying to protect Johnson Creek, which is off to the right side of the screen in blue. You can imagine all the greases, oils, hydrocarbons, crumb rubber, washing all over this expensive pavement. They had to do something to slow that down. These strips in red were basically 20 foot wide to allow for vehicle parking. The design of this included basically a prepared subgrade. There's a thin geogrid at the very bottom. There's a 6-inch infiltration media compacted. We like to see a sandback grass sod on top because it doubles the infiltration rate over a clay backside. Pretty simple installation. Here you can see it, work in progress. They roll out the geogrid. The mix is placed on top of it. It's tracked in place and compacted. Just prior to sodding, you want to charge that water fully with water. It's not done here in that slide, but that is an important step because of the quick drainage of this media. You can tell it can take any type of vehicle parking on it. So this mix was tested in the lab, basically 20.4 inches an hour, compacted at 7.5 pounds per square inch. Actually now these parking areas during games or events, they get striped in paint. So you're paying for this spot. These green areas fill up quickest among all the parking areas on the campus because people like to tailgate in grass where it's cooler, more comfortable. They do have catch basins along some of these areas to trap water in big rain events, and they did have filters on it, catch basins, to further control the runoff before it entered that Johnson Creek system. The last project I'll show you here is at DFW Airport. We've done a number of jobs there. As you know, airport grounds, some of the sites there, if they are holding water, they're going to be attracted to birds, and birds and wildlife do not go well with planes taking off. This is an enhanced swale between two active runways where you're getting a lot of runoff from the adjacent areas. This is basically the same mix, 65% expanded shale, 35% sandy clay. The architects here chose to use 6 inches of pea gravel wrapped in filter fabric, which sometimes I just see at the very bottom rather than on both sides of the pea gravel layer. There's 3 perforated pipes at the bottom, and there's 8 inches of this infiltration media. We are actually going in some designs where we're using our finer gradation of expanded shale in that bottom layer and substituting that 8-inch layer of infiltration media with 4 inches of lightweight infiltration media, basically solving the same issue. This is a shot of it going in with the fabric on top of the pea gravel, the mounds of lightweight aggregate mix to the right. This is being placed in from the sides. Once that tractor is done, it's pretty well in place. They do have catch basins on this, capturing runoff every about 400 foot. This media was placed as is, and you can tell the moisture in the media by the darker color where the swale is at. This is during laying the sod, and you can tell again the moisture holding capability of the expanded shale and sandy clay loam. It's holding water. You can visibly see that line on the edge of the swale there where it's been watered as far as the eye can see. That concludes this section of projects in Texas, and I will turn it over to Chuck Friedrich. We'll talk about projects in North Carolina.
Can you all see it and hear me?
Yes.
Very good. And we will reverse it again. Get a backwards preview here. All right. If everything's set to go, we will go. Most states have a different criteria for bioretention media. They have a guideline, sort of like their voting rules and regulations. It's the same thing pretty much with bioretention. It's across the board. Every state is different. We're looking at North Carolina here, which started out as just a sand mix with organic, and they didn't really qualify the sand. Other bioretention medias around the country refer to a topsoil. Well, what is a topsoil? It could be anything, and they don't necessarily break that down as a sandy loam or a sandy clay loam or anything like that. So it confuses a lot of people when they install these, and the ones that fail, what do they have as a defense? They don't, because it's all based on infiltration. So it's better to actually give you an advanced gradation on infiltration rates on what to expect in these medias. So in the state of North Carolina, they refer to an ASTM coarse to medium wash sand or equivalent. Well, what's the equivalent to ASTM C330? Well, it's a concrete sand. The only other equivalent would be an AASHTO spec, which again is the same thing. So fortunately, ASTM C330 includes lightweight aggregate. And we were able to have North Carolina put in a lightweight aggregate opportunity for making a media mix. And we were able to match up a C33 coarse to medium. The other thing they asked for is a silt clay fraction. That's for cation exchange. When you use a sand really doesn't have much cation exchange to attract nutrients. In North Carolina, we have a problem with phosphorus. So they want to minimize the amount of phosphorus leaving a site. So use of compost with high phosphorus is not recommended as the organic portion of this. They want a 30 index or less. So most of the time they recommend they find pine bark, composted pine bark at a 10 to 20% by volume would equal a 3 to 6 by combusted dry weight. So you can easily get by with a 5 to 10 compressed weight volume of organic. So they require testing. They want you to test almost every batch, but they've gotten away from that when you're working with a consistent company. The silt and the clay content can be reduced because using ESCS, that does have a cation exchange. Most are above 12, which will retain that phosphorus and nitrogen in the media. The sand, silt, and clay content would match what they're asking for, but fortunately, we don't have to add the clay or the silt to the media because we'll have a fine apparatus of probably around 11%, which will fill that clay and silt content, which is an advantage because it's not something that'll break down or cause any clogging. So there are advantages to the C330 specification. And this comes out as a loamy sand when you get an equivalent for a native soil. The other thing that's real important is the infiltration rates. Over time, these things will compact on their own. Vibration, rain, foot traffic, maintenance. So you want to start with a higher number because it's going to reduce over time, especially when you have silts and fines washing into these cells. So with a C330, you're going to get about a 16 to 21 inch per hour infiltration rate. Originally in North Carolina, they wanted that to start out at 2 inches per hour. And then over time, these things would slow down to almost nothing. So they've increased that to having a positive infiltration rate more than 1 inch per hour. So that more means you can go as high as you want. The problem with that is if you're just using a sand blend, you have to have at least a 24 to 48 hour retention time to denitrify the effluent coming in to try to reduce that nitrogen through just simple evaporation in the air. The other thing is the phosphorus. You're going to have some amount of iron or aluminum within that sand to have that retention. So fortunately with ESCS, we're going to remove 98% of that phosphorus or retain 98% of that phosphorus from the effluent, even without plants. So it has a real positive advantage there. This was one of the first projects done in North Carolina with ESCS, probably in the country. This was 2005 with NC State University's Department of Biological and Agricultural Engineering. Dr. Hunt worked with Graham High School to deal with their pollutant removal from the parking lot. In the upper corner there, you can see they just basically dug a pit, put some drains in it, used the media, and then used the sand-based sod on top. It is still functioning today after all these years, 17 years, and they're real pleased with that. And they just used a Bermuda turf on top. We also like to work with the College of Design, work with the landscape architects to develop and design these on campus. This particular one won an award. It's called the Artist's Backyard Owen Storm Refuge. It's between two dormitories. It takes all the water off the rooftops, the parking areas, and the hardscapes. Also, they were able to mess around with different types of plants to see which ones function and which ones do better than others in wet and dry conditions. Because you got to remember, when it rains, these things are flowing water, and when it's very dry, they're not irrigated, so the plants have to survive. The benefits of an ESCS size particle is the aeration allows the roots to go as deep as the profile, and the deeper the roots, the healthier the plants. Here it is in 2015. The plants in function are doing just great. They're different varieties. You can see it's almost like a botanical garden on bioretention plant materials. Up close, you can see the downspout. Water goes right onto the concrete pad and into the system. Another thing we looked into with the state of North Carolina, this particular job is a hospice in Cary, North Carolina, near NC State grounds. And what they're doing is they're collecting the water in a 50,000-gallon cistern and reusing it to irrigate during dry periods around the grounds of this property. So they lined it with the filter fabric, and they put a cistern underground and put the media on top. And they lay down a Bermuda grass sod. This is wintertime. That's what Bermuda grass looks like in the wintertime. And you can see in the very center, that's where the water goes, and it's full right now. So they had to draw that down to test the system, and the water came out crystal clear. So we're removing a lot of the suspended solids from the site, and they were able to run this system right into the filters and through the irrigation without causing any issues. Here it is 2 years ago, still functioning fine, no standing water, and filtering as well as ever. And as you can see up around the building, the plants are all looking healthy from the irrigation water. And remember, it's pulling all the nutrients off the site. So they're not fertilizing this. The fertilizers are coming down off the runoff and being trapped in the system and being removed. This particular study was done with Mecklenburg County. This is a recycling center and collection area for refuse and trash and yard waste. So they did two systems. They did a ESCS system, a C330 mix, and a sand soil mix. You can see the green side is infiltrating, and the other side had that requirement for the 24-hour denitrification. So they want that water to stand. The difficulty in that was when you have heavy rain events and the water hasn't drawn down yet, it's going to overflow. And when it overflows, your oil and grease is going to go right back out the discharge into the creeks. So what they did here is they put in a forebay to collect all the sediment. And what was happening is when it rained and then another rain event, it flushed all those solids back onto the grass and clogged the whole system. Whereas in the C330 mix, which is a expanded slate blend, you had the drain quickly, and the water is contained within the system. So you had internal storage. So you didn't have to deal with that surface water for denitrification happen within the system. And we were removing 75% of the nitrogen at the site. And as you can see from the discharge point, we again removed all those suspended solids as well. The difference with sand and ESCS is the angularity. Because expanded aggregates are angular, they're trapping a lot of these sediments that normally would flow right through sand because sand is more rounded or cubular. Here's a project at North Lake Mall, north of Charlotte. where they had to remove or contain 100% of the runoff off this site. So these cells are all within the parking lot. And the plant roots provide a perfect environment for the microbes to flourish around these root systems to feed off the sugars. And they expand and grow, and they really deal with the oil and grease off this parking lot, because these microbes eat that and dissolve it, and also the nutrients from the landscaping, and provide nutrients for the trees and the plants. So they feed each other. And without the plants, you're not going to have that microactivity, and you're not going to have that uptake of those nutrients. This particular site had an awful lot of these, and the good thing about it is it's part of the landscape. It's not just an empty cell full of weeds behind the back 40, which no one can see, which there are an awful lot of those types of bioretention. They just find a place out back and put grass on top of it and let it go to weeds, and it functions fine, but it just looks terrible. Where in this case, you have landscape ordinances you have to deal with within a parking lot. You have to have a certain number of trees, you have to have a certain number of shrubs, and this way they form two functions at the same time. They fulfill the landscaping needs, they're aesthetic, and they also deal with the runoff. So it's a win-win for this project. You also deal with all the nutrients. And here it is in May 2019. We refer to these basically as a BMP, best management practice. Well, it does too, both aesthetically and functioning. Here's a BMP renovation in Cary. Debbie Stringer worked with this project with our company. And they had a system in there that failed. That was the earlier sand mixes that didn't have a real gradation to them, and they clogged over time. So they took it all out, which happens a lot. We have not had one with ESCS fail, so that's a good thing. And they just fill it with gravel, put the drainage in, use a choker sand instead of a filter fabric, learned a lesson on that, and then came in with the C330 expanded slate fines and organics, which was pine bark fines, aged pine bark fines. They planted. The state also sometimes requires a triple hammered hardwood mulch, which helps with denitrification. In other words, the breakdown of the lignin in the mulch uses a lot of nitrogen. The problem with this is you got to maintain that mulch. That mulch will eventually decompose and create a lot of slime underneath and can be impervious. So if you find these systems filling up with water and not leaving after 24 hours, just go in and remove the mulch and replace it, and you'll find it's working just fine after that. We've seen that happen before. The Department of Transportation wants a higher infiltration rate. They do not want any standing water for fear of an accident. If a car rolls over into the water and obviously somebody can't get out, it's upside down, they're going to drown in this mess. So they use filter fabric. They use a coarser ESCS to allow that water to infiltrate quicker, but it's still contained within the system. And they do have their own environmental unit in North Carolina. So as long as they keep their nose clean, the State Department of Environmental Quality won't come down on them too hard. And here it is, again, it's just a maintained lawn. They just mow it with the rest of the weeds and stuff that grow into it, and it's functioning just fine. And they do a lot of these around the interstates, especially in interchanges. This is in Elon University in Elon, North Carolina. This was a problem place. They were developing a new softball complex, and they needed overflow parking for the football field across the street. The problem was this job was not finished yet. They still had construction going on. And the key is when you're doing a bioretention cell is to get all your erosion control in first, get your grasses planted, and then put this in last so it doesn't get contaminated. So you can see they did everything correctly, put the plants in, have the media in there, but obviously the softball field is still being built. You can see all that red clay. Erosion control kind of failed a little bit. You had the parking lot coated with a red clay silt, and they had to wash it off for the football parking, and it would go right into the bioretention cells. Well, this is not a good thing. This is referred to as a erosion control breach contamination. The state normally would come in and make you take it all out, start all over again. In the case with this, you're dealing with that angularity I referred to earlier. The particle shape traps the sediment on the surface, so it can be easily removed. you can just scrape a ½ inch to an inch to 2 inches off. And as you can see in the lower picture there, it peels right off and it's gray underneath. This material does not pass through that interlocking exchange of porosity and angles and void space that makes the stuff work. In the upper corner, you can see how high the water got when it was sealed up by that silt. You just, normally they would make you take the whole thing apart, but in this case, the inspector looked and the contractor showed that underneath was perfectly clean. And you can see that's only about a ½ inch of material that was contaminated. So here it is in 2015, same plants, all doing fine, project finished, everybody happy. So in conclusion on this part of the program, in review, the advantages of expanded shale, clay, and slate for bioretention media is the cation exchange is above 12 in most cases for nutrient retention. It is inert. It doesn't really affect the pH of the plants. It's not a buffer, so it'll start out at, say, 8.5, but when you add the pine bark fines, it'll drop back down to about 6 to 6.5 is ideal for plant material. 7% or a 7 pH is fine for turf. It's basically not a buffer. It's not a line. Particle shape gives you a lot of surface area along with the voids. You have filtration capabilities for removing totally suspended solids, as we saw with the bottles of clear water. We got water retention for internal storage, so you don't need to have that surface problem where if you get another rain event, that oil and grease floats right out. In this case, it's contained within the system. We got porosity and voids for aeration, meaning deep roots. If there's air, roots will grow. If there's no air, if it's saturated or anaerobic, you will not have root systems down there. We have seen systems that flood and do not perk, and the root systems are in the very top 6 inches and they can't grow any further down. In these cases, if it's 30 inches, we got 30 inches of roots. Big deal for maintenance because you don't have to water it and it's going to be durable. The product is durable. It does not break down, does not have to be replaced, doesn't fall apart, it doesn't turn to muck. It's very lightweight. For trucking and labor, you can put an awful lot in a truck. If you have to travel long distance, that's a big money saving. And the managed gradation is consistent. You don't go into a sand pit and have a totally different gradation with this. It's a manufactured product and it's very plant friendly, which all of the above, obviously. Deep roots equals sustainable plants and systems. The last thing we'll discuss is industrial stormwater. It's a totally different animal. You're dealing with some hazardous waste, perhaps. You're dealing with oil and grease, fuels, things that you don't normally want to end up in a creek. This particular project is in Chattanooga at the Norfolk Southern Yard, maintenance yard, and they created a level area to take off all the runoff from the shops where they clean machinery and work on engines and clean out cars, and that runs into this drying bed. It's covered, it's concrete. They fill it with the material without the pine bark fines because we're not growing plants in this thing. We're just basically creating the filter cake. So you got 3 layers of medium coarse and medium limestone and washed daylight, which is the expanded slate. And the MS16 is basically the C330 size, the C33 on a normal sand. Now you can see the effluent comes in, it's filthy. You don't want to be swimming in that. And you can see when it dries out, it turns into a filter cake, sort of like a flat at the desert. And they just scrape that up and eliminates the dry sludge effectively. They just pick it up, put it into a 55-gallon drum and send it to a landfill. And the effluent comes back out. This does not go out into a creek. It looks good. We don't know really the metals content or what's in this. So they do collect that. So it doesn't go into a creek or anything. But it's very efficient and it's consistent. They don't have to replace it very often because like in the other picture, it's just on the surface. It doesn't fall. All that gunk does not get down into the main filter. So I really appreciate, we appreciate the people that did the talking here. We had a good group. If you all would like to ask questions, we would really appreciate some because we have time left. Let's see, we got easily 10 minutes. ask any question you like. You can put it in the chat box or take your mic off and ask us about what expanded shale clay and slate does and other applications, where we are, what we do, and anything about the slide presentation you saw. Thank you very much.
So we have one question. Is there much difference between expanded shale, expanded clay, or expanded shale when used for stormwater?
Who wants to answer that one?
Generally, I would say there's not much difference. There may be a little bit difference in absorption rates. All companies have larger gradations and smaller gradations from which to choose. It's really based on the geographical region and what you're trying to do, but generally they all work the same. They're all used in rooftop applications, growing plants, so there's no real difference in terms of infiltration rates. A little bit difference in absorption rates, but when it's in the soil mix, there's not a whole lot of difference.
Someone else just asked, compaction issues due to heavy foot traffic?
I can answer that one. Like I showed you in one of the slides, you start out with a higher infiltration rate, and then over time, you're going to get more compaction. The joy of this material is it is interlocking, and it does not turn into a real fine material when tread upon. It's got a real strength to it. Does not break down, so you're always going to have enough infiltration for these systems to be within compliance. The other thing is it supports a lot of weight, so there's not much even heavy equipment that'll crush it. So you're going to lose about 22% if you compacted it fully. So say you filled up 10 inches, it's going to go down to about 8 inches is all you're going to lose as far as volume. So compaction, you're just going to reduce the volume during construction and installation, and then over time it'll settle out on its own otherwise. But you can't hurt the stuff by walking around on it. No.
Okay, someone else asked, what is the lightest lightweight aggregate available for green roof media application?
I would believe that would be the Arcosa banded clays. What you want to be careful is that you're going to go between the media itself is what you measure. The actual aggregate by itself is going to be between 38 pounds and say 55 pounds a cubic foot. Then you got to mix it with something. Obviously, you're not going to grow directly in it. But then it also depends on the absorption of the material. Obviously, the more absorption it is, the more weight it's going to gain from water. So they kind of balance out between the three different materials. You don't want it to be too light on a roof garden because one, it'll either float out, or two, it'll blow off the roof. So adding a little sand to help increase that density is important. Too many designers are wanting super, super light green roof media, but there's this thing called uplift. And when the wind goes across the roof, it actually picks things up. So you don't want it too light, and obviously for reasons for construction, you don't want it too heavy. So you got to have a happy medium there. So to answer your question, yeah, you can start out with a 40-pound material, which is an expanded clay, and go into the shales, which are closer to 50. But the expanded shales and slates don't absorb as much water, but they do retain a similar amount, which is available to plants. So it balances out pretty much. But again, you can adjust it with the amount of sand you add to it.
And generally, rooftop manufacturers are sourcing material by region, just based on the trucking alone. That can add to the cost pretty quickly. So they're sourcing whatever material is local to their region generally, and working backwards from that into a mixed design.
Another comment was, love the example projects illustrated in North Carolina as part of the landscape. do you have any similar projects in Texas as examples?
We probably do. The way we work in Texas, we sell our lightweight aggregates to a lot of soil blending companies, both in the Dallas-Fort Worth region, Houston, Austin, some parts of San Antonio. So when the when the material leaves our plant, 90% of the time, I don't know where it's going in terms of a landscape project or beautification effort or even a bioretention cell. Some of these bigger projects, when they're ordering, a lot of material, then I get clues to where it's going and what the project type is, and that way I can track it. But generally, I would say there's a lot of them, but you have to search landscape architects across the Metroplex to find out where their projects are at.
And another question is, can you discuss the moisture holding range of ESCS Engineered Media?
That depends again on the gradation. I can speak with some of the stuff from Texas. Basically, the 3/8 material was tested in the lab to absorb approximately 30%, but that's in a lab controlled environment. In the soil, I would say it's more or less 20%, maybe 15 to 20%. If you do go down to a finer gradation, that has been tested in the lab to be 40% moisture holding, which would work better, I would think, in a turf type soil, even a landscape bed application. But again, in the soil application, it's probably going to be where it's 40% in the lab, it may go down to 30% in the soil, just based on those different environments.
The other thing you got to take into consideration is the difference between absorption and retention. Retention is water going into the voids in the aggregates. Absorption is being held tightly. In other words, it's like a sponge. You got a lot of different size holes in a sponge, where if you turn it upright and poured water on it, you can see the water in the voids. And then there's absorbed into the material, you don't see the water. So you could get as much as 45% water retention, but only get, say, a 12% absorption. And what happens then is you got to deal with the pressures of what the roots need to get out of that. So if you have a high retention but low absorption, you're having a lot of what we refer to as available water through a curve, a tension curve. So there are different ways to look at that. As far as bioretention goes, it's different than you would consider for, say, a roof garden, because with a roof garden, you have to worry about the weight of that water, where in a bioretention you don't have to worry about weight at all. So there's different ways to look at whether you want a lot of retention or a lot of available water versus absorbing a lot of water and holding it.
And what is the name of the aggregate that weighs 40 pounds per cubic foot if I want to buy?
That's Eric.
Yeah, it's you can call me our coastal lightweight. I can put you in touch with our plant and the gradation on that. But it is very light. It does absorb water very well.
Okay, and is the aggregate typically used by itself or in combination with other soil components?
It's used in combination. It depends on the state. If you're just doing a sand filter, it would be used by itself or for just a drainage area. If you're putting turf on it, you would obviously want some form of organic in there to help. If you're doing plants, you may want to add a little compost. Depends on the state and what the requirement is. But in general, you don't have to add natural soil. We don't recommend natural soils on rooftops for sure, because you don't know what you're going to get a lot of the times. And with bioretention, you don't want to add too many fines. You don't want to add too much nutrient to it, because you don't want to contaminate the outflow. You're trying to remove nitrogen, not add it, and phosphorus in most cases. So we got to think about the microactivity and why it's important to add an organic content. But yes, you can just use the straight ESCS and then maybe a 20% by volume of organic. And that organic could be either compost, pine bark fines, but you want something that's decomposed. You don't want to start out with something that's too green because the plants are going to do well with that. So it would be typical of, say, a golf course green mix where they do have % organic.
Okay, looks like one more. Can you speak to the quality of compost and how it affects the performance of the system?
Well, there is a standard for compost, the Compost Council. And if you have to test, especially for bioretention, you have to test because of each state has a requirement on how much phosphorus is allowed in the system, how much nitrogen is allowed. So you want a compost that's going to show that it's done. It's fully composted. The good thing about the compost is it's the microbes that are so important to have it in the system. But a lot of states don't allow compost because of its nutrients, and we really don't want to have contamination of a system that's pulling a lot of nutrients every time it rains. But compost is good, and especially yard waste. I don't think you want to go with a biosolid, which is going to have some other things in it. We don't want to add metals. We don't want to add contaminants that don't break down, like pharmaceuticals and stuff like that, or from sewage sludge. You want to go with a clean. You don't want manures, obviously. You don't want heavy manures in these systems. But a clean yard of food waste is always a good additive. But yeah, you got to test. You got to show what nutrient levels are there and make sure it's finished. You don't want a green compost, that's for sure.
If there are no further questions, I would like to thank the presenters for the great presentation, and thank you to the attendees for joining us today. We'll be sending out a survey following the webinar and would greatly appreciate your feedback. Certificates will be sent to those who requested them, along with processing any applicable AIA or ASLA credits. And we hope you'll join us for any of our future webinars posted on our website at escsi.org. And thank you again, and enjoy the rest of your day.